All right, welcome to Complex Analysis. It is October 21st, 2015, about 10 o'clock. That clock seems to be a little bit fast. And so what I want to do today is I want to finish covering the proof of the Weierstrass product formula. Now, not surprisingly, when you have big results like this, there are many different ways of proving it. Anybody know how Weierstrass got his start? I believe he was originally a teacher. And then later on, he moved into the university system. We're not going to go with his original proof. We're going to go with a different proof. So the Weierstrass product formula. And so what it says is the following. Given a sequence of zeros, z1, z2, ... such that z1 in absolute value is less than or equal to z2 is less than or equal to ... and zn goes to infinity, there exists a holomorphic function vanishing here and nowhere else. And so I'm going to assume by this that we have the correct multiplicity at all the zeros. So if my zero occurs 55 times, I'll write the 0 55 times in my list. Okay? Is the answer unique? No. So it's unique up to a multiple of the form e to the g of z, g is holomorphic. Which makes sense, because we know that if you exponentiate a holomorphic function, it's never 0. We don't expect to be able to do better than that. So if we know the zeros of a function, this is the best statement we can hope for. And so I'm going to give a proof by an American mathematician. Anybody know the first American scientist truly to be respected in Europe? I'll accept 2 answers. Liberal arts students, come on, you've got to be able to give me some answer. American scientists the Europeans respected. I would say Ben Franklin is definitely justifiable. He also was extremely popular in France. And so that helps. But Ben Franklin was definitely respected for some of the work he did. I think the first real American scientist of note is Josiah Willard Gibbs. And you might have heard his name in a physics class and a stat mech class. I'll admit I'm a little bit biased because I went to Yale, and Gibbs basically spent his entire life in New Haven and Yale. But for a long time, the research was being done in Europe. What I like about the proof I'm going to give you is this is one of the first proofs by an American mathematician of note. So this was by Emmett in, I think, 1885 in the fledgling California system. So how old is Williams? When were we founded? Something around that, 791, 92, something like that. Berkeley was 1867, something along those lines, just after the Civil War. So it was a while before the American mathematics community really got started. We have the East Coast schools, but it takes a while before things start happening on the West Coast. All right, so what I want to do is I want to do the proof. And so in his honor, we're using the letter E for these functions. So E of z is related to the log function. And it's going to be defined as follows. I'm going to put a little subscript here. And E0 of z is 1 minus z. E1 of z was 1 minus z e to the z. E2 of z was 1 minus z e to the z plus z squared over 2. And in general, e to the k of z is equal to 1 minus z e to the z plus z squared over 2 plus yada, 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 plus z to the k over k. And the idea is we're going to evaluate e sub n at z over zn. So we talked a lot last time about, do we want to write the factors as z minus zn or 1 minus z over zn? 1 minus z over zn has much better convergence properties than z minus zn. Because our sequence zn is going to infinity in absolute value, by putting it down below, things are going to be good. Where is ek going to vanish? It's only going to vanish when z equals 1. So if we put in z equals z over zn, this will only vanish when z equals zn. This is an exponential factor here, so it won't vanish anywhere else. The idea is we're going to take a product of these functions. And the idea is that this product should vanish where our function is supposed to vanish to the correct multiplicities and nowhere else. Now, we don't have to be exactly the function we're thinking of. We could be off by an exponential factor. If we want to have a product factorization of the actual sine function, this matters. But if we just want to have some factorization that we can play with, then we can be a little bit more forgiving. Okay? And so the goal will be to study, let's call it f of z will be a product, n goes from 1 to infinity, of e of n z over zn. So whenever you look at a product, you can have finitely many things doing whatever they want, so long as in the limit things become nice. In the limit, what do these terms have to look like? They have to look like 1. So we need the limit as n goes to infinity of en of z over zn to be damn close to 1. Why can't I just say close to 1? The rate at which it approaches 1 matters. Remember, we had those two products last time. One product converged, one product diverged to infinity. It's not enough that this goes to 1. It's got to go to 1 with some speed. And if you look at what's going on here, if you look at this, we have basically the Taylor expansion of negative log of 1 minus z. And so the idea is that 1 minus z e to the z plus dot 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 plus z to the k over k, this should be e to the negative, e to the log z, log of 1 minus z, times e to the z plus dot 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 plus z to the k over k. Well, as long as z is less than 1 in absolute value, we can Taylor expand. And so this would be e to the negative, e to the negative z plus z squared over 2 plus z to the k over k, dot 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 going off to infinity, e to the z plus z to the k over k, if, say, the absolute value of z is less than or equal to 1/2. I never want to be just on the boundary of where things converge, because if I make a mistake, then I'm dead. So let's give myself a little wiggle room. Is it reasonable to expect that we're going to be evaluating this at points that are less than 1/2? Well, we're going to be evaluating it at z over zn. For fixed z, zn goes to infinity, so eventually z over zn will be less than 1/2. And there'll only be finitely many times when it's not less than 1/2. And for those finitely many times, well, we only have finitely many factors, not a big deal. All right, well, now we have this exponential. I want to basically just say, oh, look, I've got a finite product here. Let me just take that finite part over here and cancel. And so we get e of z over zn is going to be e, now I want to make sure, to the negative z to the k plus 1 over k plus 1 plus dot dot dot. OK, so now what we want to do, we're not having good luck with the swiveling today, so let me try moving it forward. So what we want to do now is we want to analyze this expression. Well, if we think it's close to 1, let's look at 1 minus that. So 1 minus e of z over zn is just going to be 1 minus e to the negative z to the k plus 1 over k plus 1 plus yada, yada, yada. OK, well, we can Taylor expand the exponential function. Now, we should probably be a little bit careful. If we're going to Taylor expand the exponential function, we want to make sure that we're not evaluating it at plus infinity. All right, so these batteries, this is why it's no longer swiveling. Backup batteries. So Do you think the exponential is going to be at a finite or at an infinite place? What do you think? Are we going to be evaluating at an infinite place? Finite. So we need to show that z to the k plus 1 over k plus 1 plus that whole thing is converging. All right, so how would we show that this is converging? Well, so now we're good. Okay, now it's finally swivel. So need exponent finite. Well, the exponent is going to be the sum, say m goes from k plus 1 to infinity of z to the m over m. Well, this is going to be less than or equal to the sum m goes from k plus 1 to infinity of the absolute value of z to the m. And I can even drop the m down below. I can pull out an m to the k plus 1, and so this would be the absolute value of z to the k plus 1. Then we would have a sum, I'll use a different letter, L goes from 0 to infinity of 1/2 to the L. And we're using the absolute value of z is less equal to 1/2. What can you tell me about this sum? It's supposed to. So this will be then less equal to 2 z to the k plus 1. So we do have something at a finite point. And so now if we want to look in absolute value, how much is 1 minus e of z over zn in absolute value? Well, when we expand the exponential, we get 1 plus this expression, plus that expression squared, plus that expression cubed, etc., 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 with factorials down below. Right? So the 1's cancel. We get 1 minus 1 plus, we'll call it blah. Right? Then we'll get plus blah squared over 2 factorial plus blah cubed over 3 factorial, yada, yada, yada. And because we're trying to balance things, we'll put in absolute values here. Now we just need to know how large could this sum be. The 1's cancel. This will be less than or equal to blah. So my blah is just this exponent. And now we have the sum here. Well, we know blah is at most z to the k plus 1 times 1/2. Right? K starts off at 1, so this is going to be at least z squared over, right? It's going to be at least z squared. So let's think how bad this can be. We'll have 2z to the k plus 1. Do we agree that this is going to be at most 1/2? Because when k equals 1, that's going to be the smallest possibility. We get 2 times something at most 1/2 squared. So this is going to be, if we factor out the blah, we get 1 plus 1/2 over 2 factorial plus 1/2 squared over 3 factorial. We can drop all the 1/2s. It's at most 1. So this will be less than or equal to e times blah. Or less than or equal to 2e times z to the k plus 1. Which will then be less than or equal to 2's cancel. I think we get e over 2 to the k. So when the dust settles, we see that it really is extremely close to 1. the difference between e to the z over zn and 1 is going to be something at most a constant over 2 to the k. It's extremely important that this constant is independent of k. So constant independent of k. So why does all this matter? Well, now that we have this, we can go back to our expression here. These terms all look really close to 1 as n gets very, very large. The product is going to converge. So the reason a product converges is the terms have to be close to 1, and the fluctuations about 1 have to be so small that when we look at the resulting sum. So this is writing it as 1 plus an, and we need the sum of the absolute values of the an's to converge. We have that. This is also nuclear overkill. Right? We are using growing indices down below. Emmett was not the most careful book counter. But it's fine. We don't need the most careful. We're just trying to prove something exists. We're not trying to get the smallest possible value. Why is this good? Well, the reason is, as we go further and further down, we're going to have a higher and higher power of this z, so the convergence is going to be greatly accelerated. A great question, and if you're looking at zeros, the Riemann zeta function, or things like that, is you want to say, what's the minimal n we can do? So if you look early in the chapter, there's stuff about Jensen's inequality, there's stuff about integrals and how that gives you counts on the number of zeros, there's stuff about the order of a function, how quickly can the function grow. And it turns out if the function is of bounded order, if its absolute value doesn't grow too rapidly, you can actually replace all these n's with one fixed number that's a very simple function of the order of growth. It's either the order of growth or one more than, something along those lines. And then you can make one choice of the function e every single time. What Emmett is doing is he is choosing a different one each time. So this proves the existence of a product. We can now write down any function as a product over its zeros so long as the zeros don't accumulate. Well, if the zeros accumulate, it's not even worth discussing. Okay, any questions about this? So unfortunately, we do not have all the time in the world, right? It would be wonderful if we had more time. It would be wonderful if we had a time machine. I could go back in time, start today's lecture all over again, and then, well, you already know this, do something else and do Jensen's inequality. I don't have that ability. So I have to pick and choose what I want to cover in class. And so by covering this, it gives you a sense of the material. And if you want to see generalizations, if you want to see what would you do if you knew something about the rate of growth, now you can do that. Okay, any questions on this? All right, so this is all I want to, well, it's not all I want to do, but it's all I'm going to do for chapter 5 in class right now. Maybe later in the semester, we'll come back and revisit. I want to get to a proof of the Riemann mapping theorem for several reasons. One, at some point in your college career, you should see a proof that takes multiple days to get to. I think the first time I did it took 2 weeks. I think I got a little bit better the second time. This is going to be a long proof. Second, Cauchy's just kicking Riemann's ass in terms of the number of times his name has been mentioned. So we've got to get Riemann back into the game. Third, this is just one hell of a theorem. What it basically says, the Riemann mapping theorem. And it's a shame that our student who's actually double major in physics is not here today, is if you start with a nice simply connected region, and you have another nice simply connected region, you can always find a holomorphic isomorphism between the two. We always think of one standard region, the unit disk. There is one caveat. It's got to be simply connected and not all of C. I can't map all of C into the unit disk. Okay?
So we're talking about the closed unit disk.
It would be the open unit disk. These would be open sets. And this would be the open unit disk. And so there is a map F, which is holomorphic, and then there's an inverse map, G equals F inverse, which is also holomorphic. Yes?
So you can't do the whole thing because then being entire bounded and therefore constant.
Exactly.
Okay.
So you beat me by about a minute to where I was going to go, but that's absolutely fine. No, it's fine. So I was going to say, why can't we map the entire complex plane into the unit disk? Well, as was just said, if you have f from all of C to the unit disk, so this is unit disk, if f is holomorphic, f is bounded, therefore f is constant, therefore not an isomorphism. We want to be able to map any point in here to here, and we want to hit every point here. We want a one-to-one onto function. So one-to-one onto. It's trivial in some sense to define maybe a one-to-one onto function. If you can order uncountable sets, or some axiom of choice maybe, that would be a very strange function. The point of the Riemann mapping theorem is not only can we do this, but we can do this in a nice way. And in fact, at times, you can even extend it to a nice map of the boundary. And there's the Schwarz-Christoffel formula, which I will not do. It's something like this. That's not a problem at all. This is just polygonal sides, nice angles. You can do this. This is probably the only problem I have skipped in my career as an undergraduate student. Is we were actually given a very bad polygonal region in a graduate mathematical physics class I took. I was doing really well in the class, and just was not worth the time to go out and write down explicitly what is the formula. You can write down the formula explicitly in situations like this, and it's called the Schwarz-Christoffel formula, extremely powerful. But for many purposes, we don't need the exact form. We just need that there is a connection. And again, this is one of the big themes of pure mathematics, existence. Once you have the existence of something, we can convert problems from here to problems over here. One of the big examples we often do is we take the upper half plane. So H is the upper half plane. And what this tells us is analyzing things on the upper half plane is the same as analyzing things in the unit disk, or vice versa. You can go back and forth. So what we're going to need to do is have a list of good maps between regions. If you've done physics, you've seen electricity, hopefully you've seen gravity, you've seen that both 1 over r squared forces. There are some differences between them. Electricity can have positive and negatively charged things, but a lot of the behavior is the same in the two different systems. You have the same equations that will evolve similarly. What you want to do here is you want to often solve differential equations on cylinders or planes or whatnot. And you can convert a lot of these to just one region. And if you can study it in one region, you can then invert and go backwards. Okay? So the question is, what are the good maps between the different regions? And then how would we actually prove that there always is something like this? Almost surely the techniques we've been doing in complex analysis up to now will come into play. There is another reason to do this proof. You are all supposed to have taken real analysis. You're all supposed to have seen a lot of results from real analysis. Rather than review those results from real analysis just for the sake of reviewing, why don't we actually use those results in a non-trivial way to prove a major theorem? And then that will be a good way to review the results from real analysis. Okay? So what we want to do now is we want to start assembling a list of nice maps. I want a list of nice transformations. So, nice transformations. And of course, the nice transformations, they should be holomorphic, they should be defined everywhere for now. Then maybe later we'll look at nice transformations on the unit disk. Can anybody give me a really nice transformation for Z? Not constant. I'm not going to let you do constant.
Identity.
Okay. So unfortunately, now, identity will be useful, but not by itself. But if we tweak it just a little bit, so how could you tweak the identity? There's two natural ways to tweak. So you got to build up your functions. What's a good function you can build that looks a lot like the identity?
1 over Z.
No, 1 over Z is going to introduce a pole. I mean, I know we love 1 over Z, but for now we're going to avoid 1 over Z.
Multiply by something.
Multiply by something. So we could do f of Z equals AZ. And this would be a dilation by A. So maybe over here,
Rotate.
maybe we'll take A to be, maybe we'll think about A being an R. If we did f of z equals e to the I theta z, what does that do? So this will rotate by theta, which direction? Counterclockwise is the only way to go. Alright. What else could we do?
I imagine that we could translate, perhaps.
Good, we could translate. F of z equals z plus c. So these are three really nice functions. And the idea is we want to look at more and more building block functions. Okay. Now, one thing that's nice is you can often compose functions with functions. It's easier if you map your space to itself. So let's say we have, here's some space omega, and aut omega is going to be automorphisms from omega to omega. So these will be one-to-one and onto maps from omega to itself. So let's say I have f and g in the automorphisms of omega. What can you tell me about f composed with g? Also. What is this very suggestive of?
A group.
Yeah, I mean, I've never taken abstract algebra, so for me this is hard. So we've got to check a bunch of properties. Is there an identity map? Okay, good. So the f of z equals z does come into play. We do have an identity. Do we have associativity? Yeah. Do we have closure? Excellent. Anything else?
Inverse.
We need an inverse. Well, by definition, if we define it as automorphism, does an automorphism mean it's a one-to-one onto map? So by definition, we're fine. The question is, of course, whether or not the automorphism group has anything other than the identity map. So we know it's not an empty group, but it could be a trivial group. But you can begin to see some connections between analysis and algebra now.
So is there any particular reason we're calling these functions automorphisms versus just bijections?
This is complex analysis. Do you think we ever use good terminology for anything? We have holomorphic rather than differentiable.
Because we're not preserving any structure, really. It's just one-to-one and onto.
Not an algebra. I'm not quite sure. I mean, it's a good question as to why we're choosing to use this. There's probably a good meaning behind that. That's probably worth looking up as to why we call these the automorphism group. But it's some map from the space to itself.
I mean, maybe it's still work if you just considered continuous functions, and that would be more naturally comparable to an automorphism.
Well, so of course, one of the questions is which functions are we considering here for the automorphism group? This is complex analysis, so we want automorphisms from omega, and we want them to be almost surely holomorphic. If they're not holomorphic, we really don't want to consider them in this class, unless we want to integrate against them and we want 1 over z. But we want nice differentiable maps. The Riemann mapping theorem will tell us that there will be automorphisms. Here's the remarkable fact. Imagine you completely understand the automorphism group of the unit disk. I claim you understand the automorphism group of any open set. This is powerful. This is what we do when we do things well. We reduce it to one special case, understand that case completely, and then do the general case. So, say we know the automorphism group of the unit disk. So here's my omega, here's the unit disk. So we have some map, let's give the map a name, call it M, that maps us from omega to D. We have M inverse over here. And now, let's say we have some automorphism F. So F is in the automorphism of D. what do you think would be in the automorphism group of omega?
MF, M inverse.
So if we go, how do we write it? Writing it from
Or
right to
the
left or
way.
left to right? Which do we apply first? We apply first m because we want to start in omega. We launch from omega to d. We apply m. Now that we're in d, now we apply f. Now we get back to omega and we apply m inverse. And this will be in the automorphism group of omega. And I'll let you check that. And if you take two such things of this, say f1 and m inverse composed with f2 composed with m, and you combine them, you'll get m inverse and m cancel. And so you'll have m inverse composed with f1 composed with m, composed with m inverse, composed with f2, composed with m. This will simplify to m inverse composed with f1 composed with f2, composed with m. Well, f1 composed with f2 will still be an automorphism of the unit disk. So if we can understand what's going on in just one special case, the unit disk, we can understand what's going on anywhere. Okay, so what we want to do now is we want to understand the situation of the unit disk. Okay? So we need to figure out what would be really good functions to look at for the unit disk. Okay, I was about to say it's no longer swiveling, but now it's swiveling as long as I look at it. Excellent. All right. Anybody know any good automorphisms of the unit disk?
Rotating.
I'm sorry?
Rotation.
We could rotate. Anything else?
Reflect.
Could reflect. How do we reflect?
Multiply by negative 1 or maybe something.
Okay, so we're multiplying by -1.
Never mind, sorry.
That's
Yeah, take the complement? No, it's a
complex conjugate.
Yeah,
We could take the complex conjugate, but I would have to ask you to leave this class.
Right.
Why would I ask you to leave this class?
It's not.
Because it's not holomorphic, okay? So it's not enough to have a map from the unit disk to the unit disk that's one-to-one and onto. We also want it to be holomorphic. So we all agree that these are natural starting points. The question is there anything else? So let's study automorphisms of the unit disk. I want to make sure I use the same notation as the book. Sometimes they use A's, sometimes they use alphas. I think they use alphas. They use alphas, okay. So we want to look at psi alpha of z is alpha minus z over 1 minus alpha bar z. So there's going to be a lot of algebra now, I apologize. Please pay attention because I'll make mistakes. What values of alpha do you think we can consider here? I claim that for this to be an automorphism of D, there's some restrictions on alpha you have to be able to tell me immediately. Could I take alpha to be 2? What would happen if I took alpha to be 2?
Then you could get 0.
I could get 0 down below. So I need to make sure the denominator is never 0. So what must be true about alpha? Can you tell me anything about the size of alpha?
Magnitude's less than 1.
The magnitude is less than 1. If the magnitude of alpha is less than 1, since z is in the unit disk, the denominator will be well defined. For the absolute value of alpha less than 1. So as long as the absolute value of alpha is less than 1, the denominator is at least well defined. It's not clear at all, of course, that this is going to be an automorphism of the disk, but at least it's a candidate. Is there any point where you can evaluate this function easily?
Z equals alpha.
Z equals alpha. So C alpha at alpha is 0. So if we believe, so here's alpha, here's 0, here's 0. So our function maps alpha to 0. So there's at least one point where we understand what's going on. So one way to look at this is if I have an automorphism of the disk, maybe I want to shuffle things around and I want to move the point of action to the origin. So C alpha looks like it could be a candidate for that. We want to prove now that C alpha actually is a map from the unit disk to the unit disk. So the first thing we want to show is that it has absolute value at most 1, if Z is of absolute value at most 1. And then from that, we'll then try to go on and show that it's actually a automorphism. So the first thing is it okay for me to look at the absolute value of Z equals 1? Or do I have to restrict myself to being Z less than 1? Will it be okay if I take Z equals 1 in absolute value? As long as, since alpha is less than 1 in absolute value, the denominator is still fine. I can study this function on the closed unit disk. And in fact, I could even study it, if I wanted to, on a very slightly larger open disk, if I want about the unit disk. I have a little bit of freedom. Let's look at C alpha at points e to the I theta. And let's try to do the algebra. We get alpha minus e to the I theta over 1 minus alpha bar e to the I theta. And we want to figure out what is the size of this. There's a lot of ways we can try to do the algebra. I could pull out an alpha from the top. But if I do that, I'll have an alpha bar down below. I could pull out an e to the I theta. And if I pull out an e to the I theta, I'll have alpha e to the minus I theta. That's looking like the complex conjugate of down below. So it's all a question of how do you want to do the algebra. I have deliberately not prepared most of today's lecture because I want to do the algebra fresh. I'm just saying, looking at this, I want to somehow show that it's either less than 1, or if Z actually equals 1 in absolute value, that it equals 1 in absolute value. I've got an alpha bar here. I could try to pull out an alpha, but then I'd have a 1 over alpha over here. I want to get alpha and alpha bars together. I have an alpha bar e to the I theta. If I have an alpha e to the minus I theta, that seems similar. So I'll pull out an e to the I theta. And now I'll have alpha e to the minus I theta minus 1 over 1 minus alpha bar e to the I theta. What do you notice about the top and the bottom?
One is the negative of the complex conjugate with the other.
Yeah. If I take the complex conjugate, I get alpha bar e to the I theta minus 1. So the absolute value of this, so top is the negative of the complex conjugate of bottom. So when we take the absolute value of this, it's going to be 1, and therefore we get C alpha at e to the I theta in absolute value equals 1. So what this tells us is that our map sends the perimeter of the unit disk to the perimeter of the unit disk. Do we know at this point that it maps it to the entire perimeter? No. What's annoying is it could go to just a subset. So when we're trying to understand what's going on, we have our map over here, our C alpha. We know it has to now map into the interior, into this region, but maybe it just maps into the small sector over here. And maybe we have something like this. Well, if that was going to happen, if we look at what's going on the boundary, you can try to make this argument work. It's got to be moving, and then at some point it's got to stop and then move backwards. Right? Because we now have a function of just a real variable. So maybe if you just look at the angle of this, it would have to go, stop, and come back. Because as you go all the way around, you've got to return. So if you look at this, maybe here's a question for a function of a real variable. Can you show that the derivative as a function of the real variable is equal to 0? And thus this can't happen. That's one possible approach. All right. The other thing, of course, is I'm claiming that it maps everything inside this unit disk. Do we know that? We've just shown that it maps the boundary to the boundary. So there's the max modulus principle. What does the maximum modulus principle tell us?
The maximum occurs on the boundary,
The maximum occurs on the boundary. And can the maximum also occur in the interior?
if it's constant.
If it's constant. This function is not constant, right? So that's why it was really important, foreshadowing, that we show that alpha gets sent to 0. So since there's at least one point that's not sent to something of 1 in absolute value, we know it's not constant. Not constant as C alpha of alpha equals 0. Therefore, the absolute value of C alpha of z is less than 1 if z is less than 1. So it maps d into d. And now all we have to do is change the I to an O. It's not that hard to show that this is differentiable. Okay? All right. Making progress. Want onto. So there are a lot of ways to try to prove that this is onto. One of my favorites is, I think, the method of divine inspiration. So if you give me any point, if I can just tell you the point that hits it, we've proved it's onto. So we want to find an inverse function. C alpha. And this is absolutely amazing. And I'll just put the D to tell us it's the identity on the unit disk. So if you compose C alpha with itself, you get the identity. Why is this useful? If we want to solve, C alpha of z equals some point w in D, take z equals C alpha of w, which is a D. So let's assume we have this identity. Let's assume C alpha is its own inverse. What do? We want to get to a point W. We start, so here is D. Here's another copy of D. Here's the point W we want. This will be the focal point of our discussion. Okay? So we're going to focus on this W. We need to find a point in D that's mapped to here. What we're going to do is we're going to do a pullback. We start off with our point W. We pull back to some point here to C alpha of W. So we pull back. Now what do?
C alpha at that point.
We go back to the focus. And we just apply C alpha, and we're done. So if we knew that C alpha was its own inverse, we'd be done. How do you think we can prove that C alpha is its own inverse?
Just do it.
Just do it, right? It's just a calculation. So all we have to do now is do the calculation and show that at the end of the day, when the dust settles, we have it. So let's look at C alpha of z is alpha minus z over 1 minus alpha bar z. So C alpha composed with C alpha of z, this is C alpha of C alpha of z. So it's alpha minus C alpha of z over 1 minus alpha bar z. Unfortunately, I do not do enough stories. This was supposed to be timed out perfectly so that I would say you do the algebra at home, but we've got 5 minutes left, so we'll have to try to do the algebra in public. Ah, well. So we get alpha minus C alpha of z is alpha minus c over 1 minus alpha bar z divided by,
So you forgot it.
oh, and I forgot something.
You wrote a z instead of a c alpha z to the right.
Okay, over here?
Yeah.
Oh yes, there should be a C alpha. So far I've got the numerator correct. So now the denominator is going to be 1 minus alpha bar, and now we need C alpha of z, which is alpha minus z over 1 minus alpha bar z. I have not prepared this lecture. I was not expecting to have time to do this. What should we do? To me, there's an algebraic imperative here. What do we want to multiply by?
1 minus.
Yeah, let's try multiplying by 1 minus alpha bar z over 1 minus alpha bar z, because that will clear a lot of denominators. And when we do that, we'll get alpha times 1 minus alpha bar z minus alpha minus z for the numerator. And then we'll get down here 1 minus alpha bar z minus alpha bar alpha minus z. Is there a danger that I have multiplied by 0 over 0? No, alpha is less than 1 in absolute value, z is less than 1 in absolute value, we're fine. Alright, now we start expanding everything. And when the rest settles, damn it, we still have too much time. Alright, so we're going to get alpha minus alpha, then we're going to get a minus alpha alpha bar z, minus alpha alpha bar of z, and then we're going to get a minus and a minus is a plus z. Well, this is looking good. There's a multiple of z in the numerator. Down below, we get 1 minus alpha alpha bar. And now we've got a minus alpha bar z and a plus alpha bar z, which cancels. And oh, wonderful, 1 minus alpha alpha bar over 1 minus, it does actually reduce to z. Okay? So we have now proved the existence of a non-trivial automorphism of the unit disk. So this is not to say the rotations are bad. Rotations are extremely important. This is not to put down the identity function. We need the identity function if we want to get these groups. But this is a real non-trivial example. It allows us to map any point we want to the origin. So we can basically recenter things. The question now becomes, do we have enough to completely classify all automorphisms of the unit disk? And the answer is yes. Everything is going to be related to these functions C alpha. Now, what do you think would happen if you composed C alpha with a C beta? Should that be an automorphism of the disk? Should it be the same as maybe a C gamma for some choice gamma? So I'll let you play with that and see, can you find a good way to do it? If we actually had a complete classification of the automorphisms, if we knew it was it's basically a rotation times this, maybe followed by a rotation, we'd be in great shape. All right, we have about 30 seconds left. Can anybody figure out what we've been honoring today? There is no Dr. Emmett from a California institute from the 1885. There's a reason I'm wearing a shirt from Brown today. There was a very careful reason for the choice of phrasing here. There's a very careful reason why the lecture was geared to be this today. Does anybody know the reason? Anybody recognize today's date?
Back to the Future.
Today is Back to the Future Day. Oh. So have a good Back to the Future Day.